Quest 22 Outbrief. My name's Major Tuni Massey. I work over at the Cyber Battle Lab. I'm a British Exchange officer, here for 2 years, been here a year already. My main focus for the last 11 months really has been on Cyberquest. So without further ado, I'll move on. Just to give you a quick coverage, I'm going to talk about the background to the event itself, the planning process that we go through at the Battle Lab, the different technologies. I won't go into too much depth with those, just kind of draw out what they are, broadly what they do, and how they're involved. The experiments themselves and the findings that we gathered from those experiments. I'll open the floor up to any questions or comments that you may have, and if you've got time, I can also probably cover where Cyberquest goes from here as well in the future. Okay, so what you've got in front of you there is just the mission and purpose for Cyberquest, and I'd like to kind of draw out from that mission the key points being it's focused primarily on that brigade and above level. It's looking at assessing innovative cyber, EW, tactical radio, networks, and those technologies out, whether they be in academia or industry, with a view to informing multi-domain operations, the organizational outcome concepts, and also any of the CFT cross-functional team priorities. It will also look to identify opportunities where mature technologies can be rapidly acquisitioned and follow-on experimentation can be conducted. And its purpose then is really about a live capability assessment in an operational environment that's looking to create innovation. And we do that by pushing this out. It's not a closed environment, and we are opening this up. The announcements are made to cover the vendor community, academia, and also anything that we can get from within the force as well. The bottom bit, just want to draw your attention to is any partnerships that we have. So there have been partnerships previously. This was the 7th iteration of Cyberquest. For this Cyberquest, we partnered quite heavily with the Intel Battle Lab over at Fort Huachuca, and we'll cover that more separately, but just to raise your attention to that. Okay, so the planning process itself, the 5 phases there. This entire process covers, we started this in July, and the execution was in March 22, so July 21 is when we started the preparation. Execution was in March 22. We're still going through that exploitation phase now. So in terms of the first phase, the preparation, very much about gathering the learning demands, the questions that we want the experiment to answer. And they're gathered from primarily the Army capability managers who sit within the cyber seeded, who is our primary audience, but also, as I mentioned, through the Intel Battle Lab, we had the intelligence seeded as well. So they're providing us with these questions, these learning demands, which are an expansion upon the capability gaps that they have. We then brought them together, put them into a broad agency announcement, and that was pushed out using the channels available to us to see what is available out there that can or could answer these questions. Now, the selection of technologies, there was 2 phases. We had a initial sift of papers that were produced. It then goes on to, so for future iterations, people want to be aware of this, it goes into a more in-detailed sift of those technologies, whereby we invite the vendors in, we get them to present what they have, these solutions, and then we take a rounded view. We've got all the different representatives from the sponsors of these questions, and we look to make a final selection. Normal event planning, once that's done, we're into our initial planning conference. We then move into the design element to this, and the design element, we introduced something called a bullpen session. I think it's common across other events. It was the first time that Cyberquest had done that, but that allowed us to pull in all the different stakeholders, not just those that are sponsoring the technologies, but also those that are responsible for integrating them, providing the resource, the manpower, the workforce to support this, along with any enabling technologies that we may feel are needed to to make this actually work. That was done. We then move into an experimental design phase, experimental design, and that concludes with our main planning conference, where really we've nailed down that design for the experiments, and we're ready to move into an integration phase, which can actually take quite a long time, and it did during this iteration. So the integration phase was done where we bring in the vendors, the technologies into our environment, and we look to integrate it in our environment. Because, as I mentioned, we were partnering with the Intel Battle Lab, there was an element of integration with their network as well in their environment. So it was there were two kind of locations geographically that we had to manage, but also logically we had to manage those two separate locations as well. We then move into the execution phase. Execution phase very much normal events, rock drills, COMEX, end-to-end testing, but also a receipt and training of the soldiers as well that participated in this event. So I'll cover those in more depth later, but we brought soldiers in, we had to train them up on the technologies that were being used before then conducting the serials, the vignettes that allowed us to answer the questions that were proposed. And then finally, the fifth phase is the exploitation phase. It starts with a DV Day, Distinguished Visitors Day, which was held at Fort Gordon. Lots of senior leadership were there, along with the sponsors of the learning events, and we present our findings from the event to them. But that's just the start. The reports are written, reports are generated not only to go into a forge and for others to read within defence, but reports are generated for the vendors, reports are generated for the sponsors of the technologies. So, there's a lot of reports which are generated from this, and kind of that big yellow and black feedback loop is some of the findings from there will inform future Cyberquests. They may inform future experimentation, such as Project Convergence, or they may inform, outside of this loop, future development of those technologies for the vendors. Okay, in terms of participants then, this year, the real sponsors I've mentioned were the Intel seeded and the Cyber seeded. The operational force, so the soldiers that were provided to work on these systems, were from the 10th Mountain Division, elements from Army Cyber, and also from the TRADOC. TRADOC being those that were from Fort Gordon, the Cyber Centre of Excellence. We also had a large contingent from the Australian Army who came over, predominantly EW operators, and it was a great opportunity for them because, as it turned out, one of the technologies that we were looking at, their army had just bought this technology and they were beginning to field that. They'd had no training on that previously, so it was kind of a free training opportunity for them, so it was very, very useful. The R Cyber component, I'll come on to a little bit more in depth, but they also presented a technology which they wanted to be assessed during Cyberquest as well, called LEAP, and that, although they didn't, it wasn't a technology that was sponsored specifically during that broad area agency announcement at the start. It was something that was brought in latterly that enabled many of the vignettes that were conducted. Now, covers there the different participants from the DoD, enablers, etc. I just want to draw attention to the head count. We had 139 total participate in this. You'll see the soldiers were only 22, but we had over 80 vendors present, and that just reflects the change in how Cyberquest was conducted this year. I think previously the focus has very much been on having a huge or a large operational staff. They're working on, there's been quite a big road to war scenario. A brigade staff is present. We weren't able to do that this year for different reasons. The focus is very much on identifying what are those learning demands that need answering, how do we answer them, and what's needed to answer them. We didn't need a huge brigade staff to answer those learning demands. So that reduction was made there. So that explains the numbers. And then on the left-hand side of this slide, as you look at it, you've got a big table there. That's a full list of the technologies. It's color-coded. It'll become more apparent later, but the black represents the EW, red are the cyber technologies, yellow is the Intel sponsored, and green represents the tactical radios. So we had 8 EW, 6 cyber, 2 Intel, and 1 tactical radio. Now this is a general overview, kind of a level 1 diagram, I suppose, that kind of covers how the experiment would run. Now, the tables taken from the previous slide color-coded, so you're aware of the different technologies. The icons are color-coded to reflect that as well. If I draw your attention to the bottom left as you look at it, that blue kind of squarish bubble, you've got the 2 Intel capability technologies in there. That represents the technologies that were in the Intel Battle Lab at Fort Huachuca in Arizona. Above that is, inside that kind of whitish, off-white bubble, you've got a number of technologies in there that were at the electronic proving ground on Fort Huachuca. That location was chosen because of the distances that we could achieve with some of the testing, quite large ranges. In there, the EW technologies were looking to gather data. That data would then be pushed over a tactical radio network, which we'd established using our own enabling technology. And it would go into the EW PMT server for managerial processing of the EW traffic. It would also go into the LEAP server as well, which is the R cyber provided technology, which I'll cover separately. The information from, or the data from there, would then be fed back, pushed over a SATCOM link to the, in this big, in this larger, I've not got a pointer, but in the larger blue bubble here, which represents Fort Gordon and the Cyber Battle Lab, where the majority of the cyber technologies were located, primarily the defensive Decoy, defensive cyberspace operations, and the situational understanding. Separately at the electronic proving ground, so over in Fort Huachuca, there were some cyber technologies. These were OCO-based, offensive cyberspace operations, and they were looking to sense, gather information and data and push that through the LEAP server. So you've got 3 locations. 2 of them are at Fort Huachuca, 1 at Fort Gordon. The transport between them is over that SATCOM link. Number of serials are being run in both locations, generating data, and there is that relationship, that flow of information between these technologies. Even though there are different vendors involved, the technologies we were looking to network together to allow us to take data from one to feed in and provide the opportunity for the other technologies to gather lessons from. So that was the plan. The plan changed at the 11th hour. This is the new plan. Doesn't look too different, but for the eagle-eyed amongst you, we managed to turn this around in short order, really, within a matter of days. We had moved the entire events that we had planned at EPG in Fort Huachuca, we moved that all to Fort Gordon. So even though we had some of the vendors already at EPG, they packed all things up, moved over to Fort Gordon, along with some of our staff as well. So it was quite a big effort to get that done. It worked. However, what we did lose was we lost the offensive cyberspace operations technologies because we just would not be able to achieve the environmental conditions needed to really test those systems, and also the tactical radio element as well. So the focus became very much on EW and the means by which that EW data would be pushed back to the battle lab here in Fort Gordon. But we did that, and then we'll move on. Please note, though, Intel Battle Lab still kept their experiments running from their location with their 2 technologies. Okay, so I'd just like to run through some of the technologies that we had involved in this. I'm not going to cover the enabling technologies. We'll be here all day. I'll cover the technologies that we sponsored. So from an Intel Battle Lab, perspective. They had two. Polarity was the first. It's a deep search capability that can search all source data and multiple data repositories simultaneously, and it's based on keywords and fields. It uses kind of an augmented reality type an idea behind how it works. It was operated on the unclassified open network in their military intelligence library. And the learning demand that this technology sought to answer, you can read there, but it's really how software augmented keywords search can support a commander's decision-making process. The second technology, which the Intel Battle Lab is looking at, is the BiLight's Knowledge Enhanced Tactical Analytics, KETA or KETA. It's an AI ML tool with an ontology to support analytics for the intelligence preparation of the battlefield, so IPB. This operated in the classified Battle Lab collaborative simulation environment, and the learning demand that this technology sought to answer was how AI and associated ontology support intelligence, IPB as we said, in an MDO to support that decision-making process. Moving on then to AFCEA Cyber and the sponsored technologies which they had. The first here is cyber situational understanding. This technology looks to ingest data from multiple Army programs of record to enable visualization, analysis, and understanding of cyber and electromagnetic activities. The proposed system itself is, it seeks to synchronize incident response, disaster recovery, and electronic protection plans. And the learning demands that this technology looks to provide is situated on this slide here, but it's how interoperability is handled, defined by integration with key mission systems, and assessment of dependencies and determination of the mission impact and key risk for a unit. It also looks at how the system allows users to create and track requests such as the SERFs, cyber effect request forms. Autonomous cyber is the next technology. This is sponsored by C5ISR. It looks at AI and ML to enable cyber defenders to inform Decoy decisions and proactively defend the network at machine speed against advanced cyber attacks. The learning demand there, I won't read through it, you can read through these slides, but that's the learning demand which it sought to answer. And then the final technology from AFCEA Cyber was the Keysight Threat Simulator. And I believe this had been looked at previously. It had been invited to come back to Cyberquest. Now, this is a cloud-based software as a service. It's on-prem, that's the beta version. Breach and attack simulation platform, which safely tests network and endpoint security controls against an emulated malicious cyber attack. It reveals vulnerabilities and provides various remediation options to the defender. Again, learning demands are highlighted there. Okay, we move on to EW, so AFCEA EW. They had 8 technologies, predominantly Motorola was heavily involved in this, so I'll cover a lot of their technologies, they'll crop up. But 8 technologies were highlighted there. The first one is Mastodon, from Mastodon Leviathan, and it's the prototype, so it's based on the Kraken, the TRL9 technology which they have. It's the CMOS version of this, so the C5ISR modular open systems suite of standards, so this brings that technology into that CMOS compliance environment, and it looks to employ a wideband DF antenna to provide detect and DF capabilities from within the 30 to 6 gig range. It can stream data to TDOA servers such as JICD 4.2 to queue non-kinetic responses at range. And the learning demand for this is really about that DF-in accuracy at range. Next one is Khaki's Pit Viper. This is a technology that provides a distributed, long standoff electronic attack and support capability. It enables RF collection, network survey, protocol attack, and these capabilities, or this capability, it can be deployed or employed from a very, it's a small form factor, so it can be used in UAS platforms. Learn demands there for all to read. Just so you're aware, these quad charts were used. It's the same format. I've got a little description of what the technology is. Contact details for the vendors are here if anyone is interested. But similarly, the learning demands are included as well, so you can see what each technology was seeking to answer. Black Lab, their system here, the I2C EWS electronic support payload. It's a small swap EW sensing system covering a broad chunk of the EMS. It can be used on UAS platforms and tethered platforms with TDOA methods used for geolocation against target SOIs. Also terrestrial DF, angle of arrival to queue non-kinetic responses at long range as well. It's got the same learning demands that we saw for Leviathan. Moving on to Motorola's High Tipper, it's electronic EW support technology, sensors and accurately estimates angle of arrival on push-to-talk systems, radio emitters from airborne platforms. It's the same learning demands as Pit Viper. Similar name, but this is from Motorola, is the Viper PTT. It's a software application, allows expeditionary operators both a passive survey and delivery of RF enabled non-kinetic offensive cyber exploitation effects against the modern day LMR, so land mobile radio. And like High Tipper, the learning demands which this focused on is the performance of the technology itself and also what the minimum and maximum it can sense SOI subjects of interest at altitude. Another one of Motorola's is VQ Decoy. It's a ventriloquist. The Decoy emulates tactical radio traffic across a wide frequency band, and it can be used to defensively allow a squad to move more securely in within an area, or offensively to generate false RF presence to draw enemy attention. It can be deployed and was on the UAS platform. And then finally, we've got Suppress. This is a Textron, Suppress Motorola. It's a small reactive jammer that autonomously monitors the RF spectrum, and then it focuses RF energy on a detected signal of interest. And then finally, we've got Textron's, there's the multi-domain localization with relative coordinate cross-queue, also known as the LR3C, integrated EW system that provides localization of signals, target transfer, and the prosecution in a GPS challenged environment. The learning demands were similar to answers Motorola's High Tipper and the Viper PTT. So it's focusing again on that performance and then the ability to sense at altitude, working out the minimum and maximum for that. Okay, so that's a broad overview of the technologies, the background to how the experiment was planned over the time, and also you've got an overview of how the experiment was conducted. So moving into the results and the recommendations, really the findings from this. I'll first of all talk briefly about the lower echelon analytic platform Tactical, so LEAP or LTAC. This was an Army cyber sponsored technology which they brought into the events they operated. It's a government off the shelf. The official description here is it's an AI and analytics, data ingest, storage, fusion, and visualization system for the tactical edge. It supports the deployment of capabilities developed for big data platforms, enables the learning at the enterprise level, and passing that knowledge, the analytics, and applications to the tactical edge. Now, as it states here, from a capability perspective, it's centralized data management at the tactical edge. It's got adaptive APIs that allow that pull from both the enterprise and the tactical platforms. And it's all about centralizing this data fabric and making that available at the tactical edge. So LEAP was used in our forward for us, so where that EW sensing and data was being generated, that was being pushed back into the cyber battle lab over that SATCOM link. But there was an instance there as well that was being used to ingest data from all of the cyberspace activities that were taking place in the cyber battle lab as well. So it was used as an enabling technology. The findings from this, the objectives which they sought to answer, some required more information, more experimentation was needed, but they were able to integrate it into the tactical force, support data triage and analysis from a remote location, or remote access, and they were able to pass it from data processing from the soldier platforms. So the integration occurred and the ingest of data with our Silvus radio network that was established, and it did permit the cyber situational understanding technology, which I mentioned, tool to query indicators for compromised data from the commercial feeds. Moving over to the intelligence battle lab then, a separate report was produced by the battle lab, but as a summary here, I just want to highlight they were involved throughout, from the very, that initial advertising, what our problems were, through to the execution phase as well. 2 experiments were broadly conducted, one for each, given that they were run on separate systems, slightly different learning demands associated with each. The first, though, Keta, soldiers were required to conduct the IPB process, steps 3 and 4, and evaluate the threats and develop threat courses of action most likely and dangerous for both these. And an Indo-PACOM scenario was used during the competition phase of operations to support that vignette. For polarity, soldiers were required to conduct research that would satisfy RFIs, that would allow them to perform that collect and create a threat capabilities brief. Similarly, an Indo-PACOM scenario was used for that as well. So, why this is important to the Army? Analysts must be able to conduct and analyse a deluge of data from all sources and multiple data repositories in a timely manner to support that commander's decision-making process. That was the real focus of these experiments. The findings that Keysight generated was that the Intel Battle Lab found with Keysight was that the Keysight model itself and the analytics enabled the analysts to collect and analyze data from multiple sources on multiple on operational and mission variables. Keysight also allowed the research, which would normally have taken days or weeks to be accomplished. They were able to accomplish it in minutes, and that included pertinent data related to that the analyst had not necessarily considered themselves. And also, Keysight provided that data linkage to each step of the IPB process. So some real successes in there. Polarity. The findings they found from this was Polarity can query scrape data from social media. It was able to search multiple data repositories at the same time. It's vastly reduced the collection time for the analyst to seconds, and it also provided a very user-friendly experience. It provided relevant results from deep search of multiple sources based on keywords and fields. Okay, moving on. So ACM Cyber, break this down into two areas really. So cyber situational understanding, look at first. A few objectives which were the team were looking at. So they're looking to evaluate the ability of CyberSU, the technology, to meet the minimum viable product agreed by ACM Cyber and the PEO C3T Mission Command Cyber. And the focus was on see yourself. The next objective was to obtain user feedback and evaluation on how well the system allows CMSF to see and determine mission impact and mission risk caused by events in cyberspace and the electromagnetic spectrum, and support the execution of their duties. The third was to establish procedures and APIs for integrating with mission systems encountered in maneuver units at brigade through to corps. We look to identify predefined and user-defined analytic algorithms capable of depicting mission impact based on correlation of multiple data sets, net flows, packet capture, vulnerability data and alerts, and variables such as key terrain, whether that be cyber, threat vectors, etc. And finally, to identify predefined and user-defined analytic algorithms capable of depicting overall mission risk and cyber defensive posture. And that's by correlating inputs from multiple network sources. So learning demand one, how is interoperability handled as defined by integration with key mission systems to assess the dependencies and determine mission impact and risk for a unit. So binary tasks such as identifying threats, dependencies, monitoring threats, or identifying system dependencies was successfully demonstrated through manual processes. However, sensitivity and configuration with the tactical Decoy infrastructure, the TDI, on the cyber SU depends, on which it depends, prevented the risk analytics being evaluated. However, all incidents for users had to be manually white-carded by the vendor for the users. So learning demand 2, which was, does the system allow users to create and track effect requests against the mission objectives? Short and simple answer is yes. Soldiers were easily able to and quickly create SERFs. However, the current iteration of CyberSU did not have the capability to see the SERF approvals automatically as they were approved. Instead, the approval had to be made to the higher level, and then at the higher level, that message needed to be passed to the next lower level where the SERF was approved. And learning demand 3, which is the capability in its current form likely to be used by the Army? So we'd like to note that the soldiers that were used and the audience that tested this technology was not representative of what the real user, of what the user would be in an actual CMS setting. However, the expectation, sorry. Yep. However, there are certain aspects of this that would be taken forward with further experimentation to determine, especially the asset management. Okay, that's a summary of Cyber SU, the learning demands, the three there which we focused on. We'll then move on to Cyber Decoy, so defensive cyber operations, and there were 4 learning demands which we'll focus on here. The focus areas were on whether the Army requires the ability to augment cyberspace, defenders with machine learning or automation to decrease the reaction time and the adversary's time on target. And then the other learning demand, the other objective was taken from previous Cyberquest, but it was something we wanted to revisit, and that was around the ability to emulate an adversary's TTPs to test or stress test that cybersecurity system, the processors and the personnel involved. So 2 technologies were the focus of this experimentation, as covered previously. So we had Keysight, which was provided by ECS Federal, and also Autonomous Cyber, which came from C5ISR. So learning demand 1, which was how effective automation and machine learning at decreasing cyber defenders' reaction time and adversaries' time on target. The findings that we gathered from this were independent samples of testing was used to test the mean difference between a human in the loop and the machine learning reaction times. And it was found that machine learning significantly decreased the defender's reaction time for enumeration, privilege escalation, and also lateral movement. Learning demand 2, which was focused on how can the ability of the local cyber defender be enhanced to identify malicious cyber activities. Keysight's reporting capability disclosed vulnerabilities that the emulated malicious cyber attack exploited, and recommended the implementation of cybersecurity control measures to discover, remediate, or prevent future MCA, malicious cyber activity. This provides the local cyber defenders with the option to, well, 2 options, is to properly configure the information system settings to prevent those MCA activities from happening, and or configure third-party cyber security monitoring tools, which would identify the MCA more quickly, looking at the policies, the registry, and software updates. Learning demand 3 was, can threat simulation be conducted without compromising remote system safety and integrity? So the Keysight threat simulator was able to conduct passive threat emulation using a simulated real-world exploits. These were developed by the Keysight engineers, reverse engineered. And that threat simulator removed all traces of the exploit once complete. So it left that network and the systems in the same state as prior to execution. And then finally, learning demand 4, threat emulation reports created accurately, and do they identify all emulated events? So the reporting capability informed the user, so the threat emulator reporting informed the user of which MCA techniques and tactics were successful against a particular target, and subsequently provided recommendations to monitor, discover or prevent the emulated MCA. However, the third-party tools were not available during the assessment to rigorously assess the report's accuracy. So from that perspective, we would look to conduct further study using third-party software as and when it be available. And that concludes the cyber piece. I'd like to move now into the final part, which is looking at the EW findings. AFCEA EW had the most learning demands, several learning demands here, and consequently they had several technologies as well, which I've covered. Specific technologies did not necessarily answer specific learning demands. It was a suite of EW technologies that formed the system, the experiments that we conducted. So there was definite crossover from the technologies and the experiments that we're involved in to answer the actual learning demands which were posed. The two experiments which the W team looked at, there was the technical effects using the Group 2 UAS, and they assessed this experiment looked at assessing the distance that a UAS, a manned aerial system, flying at approximately 5,500 feet above ground level could accurately sense and provide multiple electronic effects on a DMR, digital mobile radio, to inform the modular electromagnetic spectrum system, so MEMS, the terminology I'll use, and the air-launched effects and modular electromagnetic spectrum, MEMS as well. The experiment used Motorola's VQ decoys, high tipper, Viper PTT, and suppressed technologies. And all sensors were integrated into the electronic warfare planning and management tool, that EWPMT service, which I mentioned previously. That was the first experiment. The second experiment was on layered geolocation. And this looked at use a combination of aerial and ground assets to measure the accuracy of locating signals of interest using angle of arrival and time difference of arrival, TDOA, methods. It used DRS's Black Lab, Mastodon's Leviathan, and Textron's LR3C, which also included UAS, which was provided by Aerosonde. This did carry the Motorola payload, Pit Viper payload. So, learning demand 1, what should the DF accuracy range and associated circle error of probability, the SEP, value be to the capability development document? We found that lines of bearing taken from approximately 1 to 2 kilometers away from the emitter appeared to be very close to the actual locations of the emitter and the Manpack device. Learn Demand 2, this looked at the limitations of the device. So we talked about the performance, in effect, of the MEMS. We were able to record all technical details of the MEMS, and that was able to inform the capability documents, which is something we set out to achieve, so there's success there. How the MEMS, Learn Demand 3, transmitted power when unattended. So the VQ Decoy was the technology assessed here. After 7 hours, 80% of the battery life remained. Is that BB2590, I think you call them? That's the correct terminology. The experiment used 55-second duty cycle, so 5-second transmit, 50 seconds dormant. And the battery, it was able to provide 23 hours of continuous operation. Learn Demand 4 was whether the MEMS surrogate replicate unit communications and echelons above brigade critical assets on the move and the halt to project a radio frequency signal in the EMS of troop movement. So based on testing with the SINGAR's frequency hopping waveform, the VQ Decoy EMS signature was indistinguishable from the actual SINGAR's radio itself. So positive finding there. Moving on then, final 5 learning demands from EW. The fifth one was whether MEMS devices replicate frequency hops and frequency angle signals. So the VQ Decoy system, again, was used effectively. It could replicate signals from a SINGAR's radio, as previously mentioned, but in the frequency hopping mode, and this was based on the SDR used. It was estimated that the total number of hops possible was approximately 2,000 per second. Learn Demand 6 looked at how does pattern of life sensing contribute to the overall accuracy of the MEMS surrogate. Pattern of life was not evaluated during this experiment due to the time limitations and the actual paucity of allocated frequencies. And Learning Demand 7 was whether MEMS surrogate becomes more realistic with the addition of data traffic within the signal. So an RF signal with the addition of data traffic generated by the MEMS surrogate initially appeared to be genuine with in the EMS when it viewed in a spectral display. When the signals were viewed in the EMS, one could not distinguish between the real and replicated signal without embedded data. And learning demand 8, what is the effectiveness of electromagnetic attack from a MANPAC device? A MANPAC jammer operating between 50 and 20 watts was used to effectively jam analog digital push-to-talk radios at distances of greater than 700 meters in a medium to heavily wooded area. The jammer also provided was effective against FS radios. It was also used to jam a 10-watt SINGARS radio transmission at the receiver from over 200 meters away using less than 5 watts of power. And then finally, learning demand 9 was what is the maximum range, minimum power, and the receive sensitivity at range at which the system can detect signals of interest. So this is at altitude on the UAS. They were equipped with the electronic attack and support payloads. As mentioned, flying at approximately 5,500 feet above ground level. And we're able to accurately sense and provide multiple electronic effects on a DMR out to 40 kilometers, so approximately 29 miles. And that DMR was transmitting on 0.3 of a watt. So that summarizes the learning demands. Got quite heavy there with those and the findings. But like I say, the report for those that have access to the Forge will be in there. They go into much more depth as to those learning demands. But similarly, for the vendor community and the sponsors of technologies, separate reports are generated for those as well. I'd like to just kind of a couple of acknowledgements, because I do see a few familiar faces in here from Cyberquest, just to acknowledge the tremendous support that we received for this event. In particular, and I've highlighted it, it's that flexibility. We planned to do one thing, situation change. We had to rapidly adjust our plan and do something else. And it may not be big for the Americans, for you guys, but for a British guy going all the way from Arizona to Georgia is a big thing. That's like from me traveling to Russia in Europe. So yeah, well done. And we really do thank you for that support. Similarly, for the ACMs, the people who sponsor, the Army Capability Managers who sponsor these technologies, really the involvements that they had in generating those, supporting us throughout the experimental design phase is invaluable. And more importantly, looking forward, we shift our attention now towards the next iteration of Cyberquest, whatever it may be. We are looking at that. We're very much in the early planning phases, so I can't release any information on exact dates. But the intention is, I'm a planner, I'm involved in this. We'll be looking to obviously gather our requirements from across the Army Capability Managers and ensure that we've got them fixed now before we go out to industry or across academia and advertise those to you. So I'll open the floor up to any questions. If not, thank you. Thank you very much.